So let's talk about Kafka and its capabilities in detail. Kafka originally invented from LinkedIn, and as we discussed, it is an implementation of pub/sub pattern, and it is more suitable to call as a log of messages instead of a queue, and it is a persistent log. Since it is persistent, even after fetching a message, it will available on the log for later retrieval. And the log is composed of topics, and the topics are composed of partitions, and we will discuss details of it later. And this is complying with the eventual consistency model, where we will have a leader who handles all the write operations and followers sync messages from the leader to be in sync with the leader. Partition tolerance. So if we lose any node with containing partitions, it will neither affect on the consistency of the system nor lost any of the data. So looking at the Kafka cluster from 30,000 feet above, it looks like this, and it is composed of message brokers, which are actual independent servers, and each server identified with a particular IP address, and it has a particular port. And we have a publisher who is also known as a producer in Kafka world, who is sending messages, and the consumer who will be subscribing messages from the Kafka cluster. So as we talked before, the messages are stored in topics, and they are distributed across brokers within the cluster. And this topic is a data container, and a particular broker can have multiple number of topics. So what if a node goes down? Did we lose data of the partitions as per this example? It's not the case. The Kafka topics are containers for partitions. In other words, collection of partitions compose a topic. So topic A is splitted into 6 partitions as per this example, and they are splitted onto 2 brokers, broker 1 and broker 2. Now what if a particular node goes down? Still we are losing a part of data in this particular topic. So how Kafka addresses this? Kafka partitions are replicated across multiple nodes. As you can see here, the first 3 partitions 0, 1, 2 are replicated into broker 3, and 3, 4 and 6 partitions in broker 2 are replicated into broker 4. And those partitions and number of replicas are decided at the time of creating a particular topic. So now what if we lose a particular broker? So even after particular broker failure, we do have backup of this particular partitions in broker 4. So entire topic A data is retained within the cluster without any impact. So let's look at the Kafka cluster with a descriptive example. Here I have a 6 broker setup of this cluster, and let's say we have only one particular topic, and it has 4 partitions like 0 in red and 1 in blue, 2 in yellow and 3 in grey. As you noticed, each partition is replicated to 3 nodes. So when I am creating a Kafka topic, I need to define the number of partitions I want to maintain, which is 4 as per this example, and the replication factor of each partition has to be defined. So as per this example, the replication factor is 3. And according to CAP theorem, Kafka is partition tolerance with eventual consistency. And you can see each partition has a leader and set of followers. So who maintain the partitions, specifically leaders and followers, and who maintain the node and the partition assignment metadata? For that we have a special node appointed called Kafka Controller. Kafka Controller could be any of the broker, and it is continuously watching for broker failures. And in the event of broker failure, it will appoint a new leader for failed partition. And the controller metadata are stored externally, because in case a Kafka controller goes down, we will lose all the partition assignment metadata within the Kafka cluster. So who appoint the Kafka controller and who maintains the metadata of a particular controller? This is where the Zookeeper comes into the picture. Zookeeper maintains all metadata of Kafka controller and takes the responsibility of appointing a new controller in the event of failure. Talking more about Zookeeper, it is originated from Yahoo, and Kafka uses Zookeeper to store all cluster metadata. And it is stored data in a tree-like hierarchical data structure where a key value pair is created as a particular node. So talking about overall use of Zookeeper in Kafka ecosystem, it does the controller broker election, and it maintains a list of active brokers at a particular given time, and it keeps all cluster metadata like partitions and their assigned brokers. Then it does access controlling of Kafka with read-write coordinating and with maintaining the offset, which is known as the index. Further, it can maintain quotas based on the broker configuration, where it decides message consumption by specific users. Let's talk more about Zookeeper. Zookeeper composed of a group of active Zookeeper servers which is known as the ensemble. Same as Kafka, Zookeeper has a leader node and set of follower nodes. And there is a distinct difference in data nodes where the persistent nodes keep the data even after Zookeeper cluster restart, but the ephemeral data will retain until the data creator stays alive. And if the data creator goes down, ephemeral data will get lost. Kafka used this behavior to appoint and maintain Kafka Controller. So the Kafka Controller is an ephemeral node, and in the event of controller failure, the Zookeeper will delete the controller and it will initiate a request to appoint a new controller following the metadata that it has. Let's assume we have a Kafka cluster like this and the Zookeeper cluster without any appointed controller. And let's check out how the controller is getting appointed. Since no controller nodes are available in Zookeeper, all the brokers will attempt to get registered as the controller. The first broker who gets registered as the controller will get appointed by the Zookeeper, and the rest of the brokers will get an error saying node is already existing. So all other brokers will get an update about the controller broker, especially they will keep the timestamp created with the epoch along with the controller node. So as you can see here, controller node is created with a timestamp from the epoch, so it's a ephemeral node. And we will see how this epoch is used later. And the Zookeeper will start continuous heartbeats with the controller to make sure it is alive. And if you are executing this command on the Zookeeper, then you will be able to get the details of the Kafka controller like this. So in my example, Kafka version is 1, broker ID is 87 and it is given the timestamp. So this is what is used as the epoch. So what if the controller node failed? And this can happen. So the first thing that will happen is the ephemeral node will get removed. As the behavior of ephemeral node, when the creator dies, the node gets deleted. Then the Zookeeper watcher will notify the failure of the Kafka controller to all the other active brokers. Then the same process will get executed, which we discussed earlier, and a new controller will get selected with a new epoch timestamp. So as you can see, it is in blue color. The previous one which was created is in green color, and the new epoch is updated on all the available and active brokers. So what if the obsolete controller broker returns? It might be obsolete due to long garbage collection event, or it may be not reachable due to kind of network delay. Those things can happen. And it does not know anything about the new controller who got appointed with a new epoch. And it will try to write data thinking that it is the controller. And if this happens, it will be kind of a disaster. So this is where the epoch comes into play. So the broker and Zookeeper will validate the request from the controller against the latest epoch. So this is also known as zombie write. So this broker 4 is kind of a zombie. Since the epoch mismatch, then the all writes will decline, and when the zombie node recovered, it will start following the new controller, and after that partition rebalancing will be happening according to the latest broker setup. So let's talk more about Zookeeper. As we talked earlier, Zookeeper cluster composed of multiple Zookeeper nodes, which is known as a C node, and each C node is a kind of an independent active server, and as you can see, each C node is identified by a particular IP address and a port number. And this collection of C nodes is known as a Zookeeper Ensemble. And let's look at the primary configuration of a Zookeeper server. Tick time is the basic unit of single tick in milliseconds. So a single tick will be equal to 2000 milliseconds according to this example. The sync limit specifies how far a follower can be idle from the leader in ticks. The init limit is a timeout in ticks to get connected to a particular leader when a leader election is happened. The data directory holds the C node metadata, and this client port is a port which is exposed to the Kafka and for CLI based executions. And this admin port is the administrative port of the ZNode, and those are the list of servers within the ensemble. As you can see, according to this example, all 3 nodes are listed here. So each and every C node should have this same configuration. And there are 2 nodes assigned to each server. The port 2888 is used for peer level communications, like if Z nodes needs to agree on a particular update sequence, then they will use port 2888, and the port 3888 port is used in the leader election, and you can change those ports based on your requirement, and we will talk more about Zookeeper leader election later. So, out of all Z nodes at a given time, one node will get appointed as a leader and the others will follow the leader. The internal protocol used in Zookeeper is known as the Atomic Broadcast Protocol, which elects leader and keep all nodes in sync. And each node has a DB replica to hold internal metadata. And only the leader will get the control of request processor to govern the write operations. The leader and the followers will conduct continuous health checks to maintain the ensemble. So what if the leader failed in the Zookeeper cluster? So a leader could fail. Either the leader does not have adequate followers to support the leadership, or the leader is unavailable due to network latency or maybe long garbage collection operation. And the ensemble will enter into the mode to elect a new leader, and the group of nodes take part in election is known as quorum. And there is a specific formula to calculate the quorum and the optimum cluster size. Before that, we will check what's the difference between ensemble and quorum. The ensemble is number of Z nodes in the cluster, and the quorum is the number of healthy Z nodes required to perform a leader election. Q is equal to 2n plus 1 is a formula which is used to decide the number of nodes required to set up a healthy ensemble, and n is the number of nodes which could fail while maintaining the active cluster state. So according to the quorum formula, if we have one node, none of the failures will build the ensemble, and the two nodes also same, nothing could fail, and three nodes can establish the healthy cluster allowing one node to fail, and the four nodes will return the same result as 3, and the even number clusters does not perform healthy ensemble, and the 5 nodes will allow to fail 2 nodes and still maintain a healthy cluster. When setting up infrastructure and quorum, you need to be careful since it could cause the brain split problem. Like if you deploy 2 nodes in one region and other 2 nodes in another region, and if the region communication is failed, the cluster acts as 2 different clusters which will operate abnormally. And the other thing is, too many nodes in the quorum will consume more time to elect a leader. So be careful about selecting the size of the quorum. So let's look at the leader election of the Zookeeper. When the leader election is happening, Z nodes exchange messages containing Z node ID and the latest transaction it holds, and each Z node compare received messages with its own latest transaction ID. If the received transaction ID is lesser than the transaction ID a Z node holds, the receiver holds the latest transaction, otherwise the receiver is outdated. And the Z node which holds the latest transaction ID becomes the leader naturally. And once after the leader is appointed, the followers start to follow the leader, and the leader starts sending updated transaction to its followers in order to keep all the Z nodes in sync. Then the new leader starts heartbeats with the Kafka controller. So let's talk about producer. A producer will publish messages onto a Kafka cluster on a specific topic. Let's consider the same example that we have taken before with the single topic and with 4 partitions and 3 replicas. And if you look at the producer source code, when you are sending a particular message, you need to provide topic, key and the value as parameters. So by default, data will be written in round robin manner. So the first message will be written into the leader of the 0th partition, and the second message will be written into the leader of the first partition, and the third message onto the leader of the second partition, and the final message will be written into the leader of the third partition. And the special fact related to this is that there is no guarantee of the order of the messages. So the input message order will not be the same as the output message order. And if you want to maintain the sequence of messages delivered, we have to use a partition key. So according to the source code, when sending a particular message, in addition to the topic, key and the value, you need to mention the partition key. So each and every time, if you want to maintain the sequence of the messages, then you need to use the same partition key. So what will happen is, all the messages with the same partition key will be written to the same partition. And there are 3 delivery semantics such as at least once, at most once and exactly once. And it is important that the producer retries will make duplicates. Like in this example, if the producer is failed to get the message written acknowledgement, then the producer will think that the message writing operation has not completed successfully. Then the producer will retry to write the particular message. Then what will happen is it will ended up creating a duplicate message. So this is also known as the zombie writes. So you need to avoid this sort of scenario. So in order to avoid this problem, you need to use Idempotent Producer in order to ensure that you follow exactly once delivery semantic. Let's look at this example. And as you can see, a message sequence is maintained against each producer. And the producer ID is identified by the process, and upon each write the sequence is updated. And if the sequence is same, it is a duplicate attempt and the write will be discarded in order to avoid the duplicate. This is how the Idempotent Producer works. So let's look at consumer capabilities. A given single consumer can read from all the partitions. However, this will slow down reads. And each partition maintains the last read offset by a specific consumer. That way it avoids duplicate reads. And if you execute this command in one of the Kafka broker, it will display the topic and the partition along with the last read offset. A consumer can read the next offset, or it has the capability of rewind the offset to read from history. So that is one of the advantage that we have in the Kafka compared to a queue. And consumer groups is an efficient way of reading from partitions, since the consumers in the group will distribute the load among them. Like in this configuration example, you need to define the group ID of each consumer in the consumer group before read messages. And first two consumers will read from partition 0 and 1, and the other consumer will read from partition 3 and 4. So if we add another consumer, it will be kind of a one-to-one mapping of consumer to partition. And we can add consumers more than the partition count that we have in the cluster. So the advantage is that in the event of consumer failure, the group will assign the load to an idle consumer. So let's see who managed the consumer assignments. We have two roles for this particular scenario, called group leader, who is the leader of the consumer group, and group coordinator, which is one of the brokers, get appointed as the coordinator. The group leader and group coordinator will rebalance the partition assignment in the event of consumer failure. To manage partition assignments, there are two proposals such as group membership protocol and client embedded protocol. The group membership protocol uses by group coordinator, who is in charge of the coordination of members within a consumer group. Client embedded protocol will assign topic partitions to members at client side within the consumer group. And these two protocols will rebalance the consumer group and partition assignment in the event of adding or removing consumers from the consumer group. And a special note is that there are no any writes allowed while the consumer group is getting rebalanced. And let's see how this rebalancing works. This is the workflow of adding a new consumer which will initiate rebalancing. The new consumer will call for find coordinator on Kafka cluster to get the group coordinator, and it will call join group request on the coordinator. Then the coordinator will send list of active consumers and their current partition assignments to the leader of the consumer group. Then the consumer group leader will compute the partition assignments and send the proposed assignments in a sync group request. And in addition to that, all the other consumers also take part in sync group request, and ultimately all the consumers are getting their particular partition assignments as a result of sync group response. Then the continuous heartbeats will continue and the rebalance events are sent from the coordinator on the heartbeat response itself. However, there are some issues with offset commits from consumer when the rebalancing happens. For example, think we have one consumer and a new consumer is going to join the group. Then the rebalancing will occur. Let's detail out the real issue with an example. So the single consumer will be reading fourth record from the partition number 0 and second message from partition number 1, and the offsets which were read not yet committed. So while it is trying to commit the offset related to partition reads, let's say the rebalance happens, and once the rebalance happens, the partition assignment will get changed because there will be a new consumer who will be owning one of the partitions which is already read by existing consumer. And the offset which are not yet committed will not be able to get completed since the partition assignments are updated. So after rebalancing, the consumers will start from the last committed offset. So according to this example, none of the offsets are committed and it will start to read from 0th index. And this is what we call as duplicate reads. So on partition 0, record 0, 1, 2, 3 will read again, and on partition 1, record 0 and 1 will read again. So those are duplicate reads. So how can we avoid this? So to avoid this, we need to follow exactly once processing mechanism, which means we need to commit whatever the pending offsets before rebalancing is actually happens. The consumers can listen for consumer rebalance events, and in the event of rebalance, consumers should commit all the offsets which are pending to commit. And especially, as we checked before, all the reads will get paused while rebalancing is happening. And the other important thing is that the frequent rebalances will impact message processing performance because the rebalancing will delay processing of messages. So after rebalancing is happened, the group and the partition assignments will look like this. So the partition 0 will be assigned to one consumer and partition 1 will be assigned to the newly added consumer. So there are few important facts related to consuming messages. So we have the auto commit feature. With auto commit feature, consumer commit messages in equal intervals, and it is better to override auto commit and define your own commit strategy for better control. And the synchronous commits are blocking operations, and the offset commits should do in async and non-blocking for better performance. And you can use manual async commit with callbacks where the callback will execute the failure handling. So how that happens is the consumer commit the offset and hand over the error handling part to another function. Usually the async commits does not retry, because as per this example, if the first commit fails, the second one will contain the update of the failed commit. So we don't need to retry in async commit. However, the sync commit is recommended to be used in the event of error handling, like in a try catch block. Within the finally block, you should use sync commit in order to make sure that everything written up to the exception is occurred. So far we talked about cluster behavior, and let's talk about data communication into the cluster. So the producer uses a key and a value serializer since the data transmitted to Kafka is in the form of byte stream, and the consumer should use a compatible deserializer to get the actual data out from the message. And the serializers are defined with a particular schema. So as you can see here, in the schema we have error ID, error code, message, status and timestamp. And the same schema has to be used when the message is getting deserialized from the consumer end. And what if we need to update the schema? As in this example, let's say we remove the status and we make it like status code, and newly we will be adding trace ID. So then how deserialization should handle this situation? In the event of updating the schema, it will impact the existing consumers since the payload is getting updated. If the deserializer does not aware of those changes, and if it is a kind of a breaking change, the consumer will fail to compose the message correctly. So in order to avoid that, one approach is to send the schema along with the data within the same message. So the deserializer will know which schema to use in order to extract the actual data out. And to make this more efficient, there are tools available like Avro protocol buffer, which helps to maintain the schema as a kind of a remote service. And instead of embedding the entire schema within the message, it will allow you to embed only the schema ID within the payload. And this will be more maintainable, and at the same time it will reduce the size of the message. So as per this example, we do have 4568 schema, and as well as we have 3569 schema. So second one is the updated schema, and each producer will decide what is the schema that it is using, and the schema ID will be embedded within the respective message. And based on the schema ID, the consumer knows which schema to be used when deserializing the message. Let's talk about Kafka Streams. Kafka Streams allow to distribute events in a single topic into multiple other topics based on a particular condition. For example, as in here, if the messages need to split into regions based on a particular region parameter within the message, we could update them like this. So whatever the message arrives in all regions topic will get splitted into region 1 and region 2 based on the region ID attribute. We can use the Streams API to configure that, and whenever a particular message arrives in events all regions topic, it will get automatically populated onto region 1 and region 2 topics. Let's talk about what are the factors to be considered when we want to monitor a particular Kafka cluster. First thing is that if consumers are behind the partitions, it will make more time to read particular message. So the gap between publishing and consuming should be lesser. And if the partitions take more time to sync, there will be out of sync data in the cluster. And if the leader election happens frequently without adding or removing any brokers, and there should be something wrong with the cluster that you need to seriously focus on. Writing offsets should be efficient, else there will be duplicate reads if offsets are not properly committed. Related to hardware, keep constant monitoring on disk I/O since this is some sort of persistent operation. And Kafka is kind of a memory intensive program, and when the operating system is consuming swapping, which means dumping filled up data within the memory onto a disk space, will impact on application performance. And on CPU is not a kind of a critical factor, however it is recommended to use a particular dedicated CPU, otherwise you will be having delays due to context switching, because the CPU will try to consume requests of multiple applications at the same time. And you should watch for network spikes, because those network spikes could be due to unnecessary reader elections, and those can reduce the performance of the cluster, and it is better to set up alerts on those. Finally, it is required to enable cluster JMX and consume cluster events via a particular monitoring tool in order to watch any particular issues with the cluster. Finally, there are some popular tools available to watch Kafka cluster topics, partitions and cluster details. So those tools are like Kafka Manager from Yahoo and Confluent Control Center, Cloudera, Lenses, Datadog, Kafdrop like tools.